Today, my name is Tammy Reller, and I am with Teledyne Tekmar, and I know your initial invitation had it as Christina Mason, but Christina and I both work together and have worked together on this project. She is actually in Canada helping me out with something today with a Lodex install. So I'm going to be, she and I have been working on this, feels like a Monday morning. All right, so when we're talking about TOC, most of our total organic carbon consists of living organisms, decaying matter, synthetic organic products. As most of you, I'm hoping most of you are familiar with TOC on here, but generally our samples are made up of some type of organic carbon and inorganic carbon. And oftentimes the inorganic carbon is comprised of carbonates and bicarbonates. Usually the total carbon is the sum of the TOC and the IC, and we're typically using a type of non-dispersive infrared detection system for when we take the sample and we are oxidizing the carbon to carbon dioxide, and then we're going to have that read by the NDIR detector. So when we look at different TOC methodologies, the primary TOC concerns are, can we achieve the required detection limits? Whether we're looking at clean water samples or wastewater samples, it seems like most of our methodologies are pushing us to get lower and lower on the detection limit scale today, whether in our reporting limits. So that can often be a challenge for us. We definitely want the instrument to have accuracy and reproducibility. As a VOC chemist previously, one of the things that when I came into TOC was I want to see an instrument that can do, it only has to do one thing. We need to analyze carbon, and we need to do it well. We need to do it accurately and reproducibly day in and day out without any hiccups in between. So that's another thing that we want to focus on. And it has to be ease of use and reliable. Now, when everybody sits there and says, what does ease of use mean? It's such a subjective term. And so when I go and I talk to management here, one of the things they'll do is they'll challenge me and they'll say, well, what does ease of use mean? So in my terms, and from talking to customers around the globe, you know, we wanted an instrument that you know, was easy to go in and set up a calibration curve rather quickly. We want a load and go. You know, we oftentimes have issues with, we make the software so complicated. And so one of the things when we looked at the software was we looked at some of our older instrumentation and said, how, you know, easy is it to use the software? Does it take us 33 clicks to set up a calibration curve? So we wanted to make sure that we had a greater than 50% improvement on that from a time standpoint. The other thing that all of us laboratories are facing these days are consolidations. And sometimes it's not always chemists or application chemists that we have that are able to run these units. In some cases, we might have microbiology departments merging with the organic carbon analysis department and the TOC department. And so we need to make it so that everybody can just put the samples on and push start. So one of the keys to obtaining accurate low-level TOC results is we want to maximize any sample carbon response. We want to make sure that our gas is clean, that our DI water is clean, that any air that we have in our laboratories is not causing any background contamination in our samples. So when we look at two different techniques, generally we talk about combustion and UV persulfate. So combustion oxidation is where we take a sample and we're going to inject that into a furnace at around 680 degrees to 1,000 degrees Celsius. And we're getting essentially complete combustion or complete oxidation of that sample. Now, when I think of combustion, I think of very hard to oxidize samples. These would be your wastewaters, your seawaters, your brines, you know, some of your effluents and influents. Well, when I think UV persulfate, we're using a chemical to make the oxidation process happen. So we're using UV persulfate, and we're making that, we're going to transfer that sample into a sparge vessel, and we're going to add UV persulfate. So when I think of that type of analysis, we're looking at very low-level analysis, drinking water, low ppb, pharmaceutical analysis. So today we're going to focus primarily on the combustion oxidation. So when we look at combustion TOC, we know that the characteristics is that it does have excellent oxidation of all organics. We are able to analyze those very hard to oxidize samples such as salt, wastewater, surface water, groundwater. Sometimes you can have relatively high system blanks because you're using a catalyst in order to make that oxidation take place. So anytime you add something extra to a system, it can potentially give you additional background noise or background contamination that could elevate your baseline or your signals. Generally with combustion, we have better precision and accuracy at higher levels, more in the ppm, say 1 ppm and higher. It's very good for particulated samples. But sometimes people say, well, there's a lot more maintenance and cost of ownership associated with combustion because you have to obviously change the combustion tube, which takes into account that catalyst. In other cases, you may have some type of sample delivery system or an injection needle. So that's going to need cost changing. In a lot of these systems, and even our higher-end systems, you have syringes, you have 7-port valves, you have, these are all things that are needed to move the sample from one area to another. But we all know that moving parts can be costly. So we wanted to focus on something. The customer, we went out into the field and we talked to a lot of customers, both domestic and internationally, and said, give us your feedback. You know, if you were the ones having to run this system day in and day out, what is very important to you? You know, what does it really need to have? Not what does it want to have, because we all have to realize that we all have a lot of wants in life. You know, I always would like to have a lot more accessories on my car or things like that. But we also have to be realistic about what our budgets are and what we have available to be able to pay for those extras. So we focused more on what the needs were. So we needed the customers needed it to be economical. Well, in some cases, we look at economical as, well, is it the lowest cost in the market? Well, it really doesn't help if I come in and say, well, we're $10,000 lower than everybody else in the market, but on a day-to-day basis, this thing is going to cost you an arm and a leg to run. So we focused more on the low cost of ownership. Yes, it is one of the lower cost instruments that is in the market, but we really wanted to focus on what is it going to cost to run this instrument day in and day out. We needed the software to be load and go. Put the samples on, save your schedule, press start. We definitely wanted this runtime shorter. It needed to be between 13 to 15 minutes per triplicate. Maintenance, as we know with combustion, you are still going to have some type of maintenance. You're going to have to change a combustion tube every 3 to 6 months, depending upon the type of samples that you're running. If you're running fairly clean samples, you may get a year out of a combustion tube and maybe even get a year out of a calibration. But we need to focus on maintenance because most of the laboratories, most of us do not have the time or the money to be down for more than 24 hours. So we need to be able to get up and running quickly. Priority sampling was another one, to be able to put a sample in whenever needed and have without interrupting the entire cycle of the automation. And the other one that was interesting is the majority were able to export, but to be able to import a sample schedule from LIMS into our schedule, into the actual TOC software schedule. So these were the things that we focused on primarily. So if you haven't seen this yet, this is the new Lodix. But it's, I guess, really not new anymore. It's for it came out probably in the last year or so. So what is one of the most difficult matrices that we need to analyze for TOC? And that would be salt. We are going to focus the remainder of this webinar on salt and salt samples alone. I know this has always been a challenge for any TOC manufacturers because salt can present so many different problems and so many issues when looking at systems and running these as samples. One of the issues is it's going to break down the catalyst. So as you put your sample, as you transfer your sample over to the combustion tube for that oxidation to take place, you're competing now with all of these chloride ions. And we also know that chloride ions are very, very harsh on the detector. So we need to have some type of halide scrubber that is going to help to remove some of these prior to getting to, because detectors make up essentially 30 to 40% of the cost of an instrument. So they're very, very expensive to replace. The other thing with salt is it tends to build up in the combustion tube. And what that causes is now you're going to get flow restriction. And you're not going to get proper flow. If you don't get the proper flow through there, then all of your, once you do that conversion to CO2, it's going to take a lot longer for that to get over to the NDIR detector. You'll start to see problems with your reproducibility. You may even see problems with peak shape. Sometimes with salt samples, you'll see the inevitable, what we call the camel or the humpback, and you'll see that double hump peak coming off of there. You can also get corrosion of the sample pathway and injection needles. If you're typically running a sample or a system that has a syringe and a 7-port valve, all of those salts will eventually start to deposit into different places within the system, and they are going to cause issues. The question is how expensive is it going to be to replace those parts? And that's what we want to focus on, is lower cost of ownership and maintenance. So Christina and I began when we first came out with this unit, and we started running a salt study. For those of you that are not really familiar with the Lodix, it's a 30-position auto sampler, and it uses a single 1/2 mil injection loop to transfer the sample from the IC sparger over to the combustion tube, onto the combustion tube for the oxidation. So there's no syringes, there's no arms, moving parts. It uses a conveyor. So the first study that we ran, our combustion tube consisted of a 1/4 gram of quartz wool in the bottom. We were using 17 grams of a small sphere catalyst, platinum catalyst. We had 3 grams of quartz beads on top. And the reason for that is when you're using really small catalysts like that, once you inject the sample onto the top of the catalyst, it can kind of, and with a flow of about 200 mils going through a system, it can cause a little bit of disruption, and you don't want that catalyst migrating its way back up and causing any restrictions in the system. So those quartz beads are only there to hold down the actual catalyst. In some cases, they may use, as we're going to show in the salt setup, we use a platinum screen and a quartz retainer ring. On each of these, we used a 1/2 mil sample loop. The way that the Lodix injects the sample is two needles will go into the sample, and it will pressurize. One needle will pressurize the vial, and the other one will move the sample volume out of that into the IC sparger. It's going to add some acid and then purge it, sparge it. We're going to remove the inorganic carbon, and then that sample is then going to be transferred over through a sample loop. So as you can see with both of these, my cursor, we're using a 0.5 mil sample loop on both of them. The only difference is one setup has a quartz beads on top. The other one, we're using a platinum screen and a quartz retainer ring. And this is what the picture looks like. So over here on the left-hand side, you see the 3 grams of quartz beads over the very tiny catalyst, and we have 1/4 gram of quartz wool. And this is a little closer picture, 1/4 gram of quartz wool on the right, 17 grams of small sphere catalyst, try to say that 3 times, and the retainer ring holding in the platinum mesh screen. Now, the difference between these two are 3 grams of quartz beads cost about $12. A platinum screen and a quartz retaining ring costs about $112. So we wanted to look at these two different setups because previous experience with these quartz beads is that once you get salt onto them, it doesn't take very long before you end up getting a cement block, and we will see that coming up. So the method parameters, one of the things that is great about the Lodex are there are not a lot of parameters that you can change. In the default TOC mode, you have the option to change the temperature, the acid volume, your carrier gas delay time, and your sparge time. The temperature, furnace temperature, for some, they like to increase their temperature for hard to oxidize samples. When we did a little study where we increased it to 800 degrees and we really didn't see any more response, then we did it 680. So we knew that we were getting complete oxidation at 680. The acid volume is pretty much to remove any inorganic carbon. 0.2 milliliters or 200 microliters is the default volume, and that is usually good enough for up to about 25 ppm inorganic carbon. Now, the carrier gas delay time, what this is once you inject the sample into the combustion furnace, this is the amount of time that the sample is going to sit in there, and it's just going to interact with that heat and that platinum catalyst for a while before the carrier gas is going to turn on and move that sample out of there and into the NDIR. Now, sometimes if you if you had hard oxidized compounds, if you increase the carrier gas delay, what that does is it enables that sample to sit in there for a longer period of time and make the reaction take place. So with salts, because there's so many things competing for that catalyst, the only thing we changed was the carrier gas delay time. We set that to 120 seconds so that we had the optimum amount of time to make that conversion to CO2 take place. So initially, this was the calibration curve that we ran. We ran a 0, 1, 5, 10, 25, 50, and 100. And you can see these are the RSDs over here. And we had an R-squared value of 0.999. So this is what a typical report looks like for coming off of the Lodex. It prints or reports to PDF or CSV. And as you can see on day 1, we ran a check standard, a 25 ppm check standard. Then we would follow with 10 salt samples, followed by another 25 ppm check standard. Then we'd run a DI water in between. Then we'd run another check standard, followed by 10 salt samples and another check standard. And we did this for every day. We ran the exact same schedule. And the idea was we wanted to get this 25 ppm to pass immediately after the salt, so we did not run any DIs. Now, the system will automatically run a rinse in between each sample, and that way it rinses the entire sample pathway, including your IC sparger, your sample loop, your sample needle, and it does go through the combustion tube. So this is day 1 of Christina's. Christina was running this particular study. Then this is what we're seeing after 160 samples. Everything is still passing. Everything is still looking good. Although you can see on the end where the RSDs are still pretty good, but you're starting to creep up there. I'm a stickler about my RSDs, and I'm very much want them all to be below 5%. So when I start to see any of the RSDs creeping up around 4% or so, then I will start to look at doing some maintenance. Trust me, this will make your system last longer over a longer period of time. So after we had 180 samples, as you can see, we started to fail. And this was Christina's data. Remember I said here that these, down here at the bottom, these were starting to creep up around 4 or 6%. That was my indication that I think this is probably getting close to the end of its life. And sure enough, the next day, it failed immediately on the first one. And you can see the RSDs here starting to creep up, and down here we're even around 20% RSD. So this was a half mil sample loop, and after about 180 samples, that was pretty much all we could get on. And this is running on even the quartz retainer ring. So whether you're running the quartz grams or the quartz retainer ring, you're going to possibly get 180 to 200 samples out of a combustion tube, around 600 injections. And you can see on this one, so you can see, look at how big this salt plug is in this big red square here. And if you look in the yellow, the actual combustion catalyst is still in very good shape. But because of this salt plug, you end up getting some failures, because now your sample can't even get to that catalyst anymore. So what can we do? What do we do to improve it? So one of the things we could do with salt samples is we can dilute all of them. Problem is that's too much work. You know, now you're manually having to dilute all of those samples, and it's going to start to challenge the low-level detection limits that you have. So what about decreasing the sample volume? Now, that's something that's easily done if you have an automated system that has a syringe. But in our case, we're running a half mil sample loop. So we decided, hey, let's run the same salt study again. As you can see, we ran everything still the same. The only thing that we changed is we went to a 0.3 or a 300 microliter sample loop. And this is what the combustion tubes still look exactly the same as we ran on that first study with a half mil loop. 1/4 gram of quartz wool, 17 grams of a small sphere catalyst, platinum screen, and a quartz retainer ring. We kept all of our method parameters exactly the same. So we kept the carrier gas delay at 120 seconds because that is pretty much the optimal for running a salt sample. If you start going even lower, you may start to see that hump. So if you want to shorten your time down to 45 seconds, you can. You're not going to get you're not going to get as great a response. You will get accurate integration of those peaks, but if you really want optimum, 120 seconds will do that. And that puts your runtime at around, I think, we'll look here in a minute, but I think it's around 16 minutes for triplicate. So once again, we start over with a calibration curve, and when we moved to this 0.3 mil sample loop, we did start over fresh. So we started with a fresh needle. We cleaned out the glassware, and we put in the 300 microliter sample loop. We started each one of these with fresh from a baseline, so that we knew that we weren't carrying over any interference from the previous study. So we ran 0 same exact calibration points again. Over here are the RSDs, so everything is below 5%. And you can see that we're at 0.9999, and this is our y-intercept factor. So with this salt study, we were able to successfully analyze 560 salt samples in triplicate. So we went over 2 times the number of samples that we were able to run with our initial setup, just by simply going to a smaller sample loop. That was 1,680 injections. We did no replacement of the catalyst. We did not recalibrate during that time. Now, you will have to do some maintenance. the salt tends to, the Lodix has a stainless steel sample needle that goes into the combustion tube in order to deliver the sample. Salt is going to tend to corrode that injection needle. So we found that as we started to see the possibly the percent RSDs increase and creep up around 4, 5, 6%, we would take a look at that injection needle, and I have a picture of it in a couple slides that shows you that it literally eats away the bottom part of that. And but you can still continue, as long as your check standards are passing, it will still continue to deliver the sample accurately. And you can still quantitate at fairly low levels. We were also running 5 ppm check standards after so many hundred samples in order to check to see how low can we still reproducibly see when we're running this harsh of a sample through the system. Now, if you look at Christina's combustion tube now, look at the salt plug. It has moved halfway, even further down in the tube. I mean, this is a pretty good section of plug. And as you can still see at the bottom of here, if we didn't have this plug, we would be able to, this catalyst is still good and still able to be used. And you can also see it in this picture here. So the question is, well, why didn't we just dump out the salt plug? Well, we actually tried. We took tweezers and we jabbed it in there. We tried to break up the salt, and it just really, really formed this harsh plug. But overall, 560 samples, or 1,680 injections, really isn't too bad on a single combustion tube and a single calibration. So then we decided. I said, Christina, let's try something a little different. Because to me, even though we could get 560 samples out of that combustion tube, we still had the added cost of a quartz retainer ring and the platinum screen. Not a lot, but an extra $112, $125. So I said, why don't we try going back to a large sphere catalyst? And of course, since you're using larger spheres, you're going to use a lot less of it because it takes up more volume in that tube. So we went back to our setup. We used 1/4 gram of the quartz wool. For this, when you go for the large sphere catalyst, you only use 10 grams instead of 17 grams. And then we also did the study with a 0.3 mil or a 300 microliter sample loop. What we wanted to do was see if we could get just as many samples as she did with the smaller sphere and the quartz retainer ring, or even better, was there some opportunity here? So this is what the combustion tube looks like. Over here was the quartz wool, small catalyst, the retainer ring and platinum screen, and over here, all we have in this tube is 1/4 gram of quartz wool and 10 grams of a larger sphere catalyst. We actually did the carrier gas delay at 90 seconds. For this larger sphere catalyst, we were able to shorten 30 seconds off of the actual time that it sat in the combustion tube in order for that oxidation to take place. All other parameters remained the same. So this is the calibration. Once again, we ran our 0 to 100, and this will give you the absorbance counts from the detector. So you can see our RSDs are all very good, and we got a 0.9999 for our R squared value. So we are still, I am actually still running this. I set up another run last night. We are currently at 620 salt samples in triplicates. That's over 1,800 injections. I have not replaced the catalyst, and have not had to recalibrate the system at all. Now, I have had to do some maintenance to it, and I will show you in a second what we did. So why? Why are we able to get so much? If you look at this salt plug right here, it's a lot less than what we saw in Christina's. And the reason is because for some reason when you use the larger sphere catalyst, it enables you to dump the salt out of the combustion tube. There were a couple of times, and I've done this multiple times. Usually we say earlier we talked a little bit about changing the sample injection needle. And I'm going to see if I get to that picture in a second. But if you look at the combustion tube study, this was Christina's catalyst. This was her study. So you can see the salt plug starting to form, and all of this catalyst back here was not able to be used. And if I go back a few, and look, we're still able to use this catalyst because we're able to get the sample through onto this and actually be able to use all of the catalyst in the tube, which is why we're able to get more. The key is being able to dump part of that salt out. Now, this is just pretty much from 300 samples on. This is how much salt was accumulated from 300 to 620 samples. I would like to do another study where we actually measure the amount of salt in milligrams that can be built up in that combustion tube prior to having to do maintenance. So for right now, we look at roughly around 150 to 200 samples. So this is a picture of the sample needle, and as you can tell, this was after about 200 samples. I started to see the percent RSDs creep up to around 4 or 5%, which I knew then I was going to get a failure coming on slowly after that. So at that time, when I replaced that needle and the sample line, each of those cost about $65 to replace the needle and the sample line. Now, if you want to change just the needle yourself, you can do that, and it's actually, I'm not sure of the exact cost, but I want to say it's maybe around $15, $20. And you would be able to replace that. All of this is you're able to replace yourself. It literally takes seconds. You would remove the cover, the side cover, and you have automatic access to the furnace right in front of the unit. So when we did this maintenance, we would change the sample needle, and I would also, the carrier gas line that is going into the actual top of the injection block that delivers carrier gas, your air or your oxygen, into the combustion tube. I would end up snipping that and put on a fresh ferrule. That's about another $3. And the other thing that I would do is if you took that needle and turned it upside down, as you can see inside of here, we're starting to collect some salt up in that area that could possibly be spraying back up or what have you. So after, again, once I change this needle, I remove these 4 screws and I just separate this, and you really don't even have to do that. You can just pull the needle out, and I put this under some DI water. I dissolve all that salt, rinse off this O-ring inside here, make sure, you can see this is the carrier gas line coming right here in the side. There's a peak nut. Want to make sure there's no plugging going on in this little hole here. And rinse all that out, replace the needle, and we're ready to go. So after 580 samples, this was 2 nights ago, I ran, and I started to see my RSDs creeping up right here. And sure enough, what happens? My check standard failed. Now, even though it barely passed on this next one, you can see that these are supposed to be around 29 to 30 ppm, and you can see the results all dropping off here. And the RSDs are wow, anywhere from 16 up to 35%. So the next morning I came in and I dumped out more salt, and I did not change the needle. The needle was fine, but I had accumulated quite a bit more salt. So I dumped out, I just took the combustion tube out, I waited till it cooled, I turned it over, tapped it onto the table a little bit, dumped that out, put the combustion tube back in, the needle in, and turned the system back on, and began running, and lo and behold, I'm back to 620 samples. This is from my run from last night. We're back to everything is below 5% RSD, and we have now passed all of our check standards. So when I talk about how low can we go, I ran this the other day. We were up around 580. Oh no, this was one of the first ones that I ran. After around 350 to 400 samples, we ran a 1, a 5, and a 10 ppm. Now, as you can see, the 1 is out. It's more or less within plus or minus 15%, but it's just outside of that 10% range. But you can see we're readily and easily able to see 5 and 10 ppm and pass those check standards. The other day, I ran, after 580, I ran another 5 ppm check standard, and my RSD was 0.07%. And passed at 5.06. So when I spoke earlier, we said customers came back to us and they said, we want something that's economical. We want low cost of ownership. We want the software to be easy so that if we have to train other people to use it, we can do that within a couple of hours, that it isn't going to take them days to learn to use this. We want them to be able to load, set up a sample schedule, and press go. We need the run times between 13 and 15 minutes per triplicate. We need to have easy maintenance. That means you need to be able to get to that combustion furnace readily. It can't be in the back of the unit. You don't want to be having to take off side panels to get to your wet chemistry sections. We need to have a large linearity range. It makes me cringe when people say, I have to run two calibration curves, one for my low end and one for my high end. It shouldn't be that way. You should be able to run 0 to 1,000 and encompass all of your samples in between, and still be able to pass a low 5 ppm check standard and a middle range, 100 or 500 or 50. Sorry, went the wrong way. So we're giving you low cost of ownership. There's no syringe mechanisms or pumpers in here. If any of you have ever had to replace those in the system, they can run around $600 to $700. No 7-port valve, right around the same cost. There's no mass flow controller. We simply use gas to move the sample. One of the questions I get is, how much gas is it going to take? A tank of air will usually get you through 1,500 samples or 4,500 injections. And that's because the system goes into standby 30 minutes after you're done running it, and it shuts all of your gas off. So you're never left with that just sitting with flow going through the system when it's not being used. There's no expensive replacement needles. There's no carousel mechanism, meaning that there's no arm to replace. It uses a simple conveyor belt that moves around and a magnet that has a sensor that tells you where the home position is. You have an extended life of the catalyst. This system has worked great with every catalyst that we put in there. Although looking at the larger sphere catalyst and how well we're doing with the salt samples, we may start looking into doing that for all samples. And your calibration remains stable over time. So, what do you think? Do you think we can prove again? Well, we started looking how low can we go. So that seems to be the new that's the new motto for how low can we go from a standpoint of sample volume, and how high can we go with the number of salt injections. So recently, since Christina, I'm still running on the larger sphere catalyst. Christina has now moved over to running a 0.2 mil loop, 200 microliter loop, to see, can we double the number of injections again? If you remember the first setup, we had around 180 to 220 was the average. Then her setup went to 560. Is it possible by going from a 0.3 to a 0.2 that we can reach 800 mils or 800 samples? That's close to 2,400 injections. How low can we go? If we're running every time you go to a smaller sample loop, you have to realize that you're putting a lot less on that combustion, so your response is going to be much lower through the detector. So are we still able to see down at that 5 ppm? Do we have the optimum recipe for the combustion tube? Is it the small sphere catalyst? Is it better to have all large sphere catalysts? Or what about a mixture of small spheres and large spheres? You know, are we still maintaining our low cost of ownership promise with regard to the Lodex? Well, all you're going to have to tune in for the next webinar, which hopefully we will have in another month or so. And we will have that data for you. So sorry to keep you lingering. I'm going to continue running on my 0.3 mil loop. And I assume that my system is going to fail in probably another 20 to 80 samples. So that will put me at 620 to 680. So if I move to a 0.2 milliliter loop with the large sphere sample, or the large sphere platinum catalyst, could we be pushing in upwards of 1,000 salt samples? We will see. So in conclusion, the Lodex is the ultimate solution for wastewater, surface water, groundwater, seawater, or any other hard to oxidize matrices. And we've made it an economical price not only to purchase, but to own it on a day-to-day basis. And it fits and meets all of those method requirements, whether you're running 5310B or a 415 EPA method. So I want to thank all of you for your time today. If you are interested in taking a closer look at the hardware and at the system and a live software demonstration, why don't you contact me directly at tammy.reller@teledyne.com. And I do quite a few of these a week, and what we'll do, it takes about 45 minutes to an hour at the most, and we'll spend a little bit of time talking about your application in particular, and kind of customize it to what is best or what you need. And then we'll go through a handful of slides that actually look at the instrument and the insides of the panels, and then do a live software demonstration for you. So if you hold on, we're going to look and see if we have a list of questions. So the question is, one of the questions, for saltwater analysis, you have to buy a separate combustion tube. Right now, we're still running the research on that because I haven't decided whether or not we know that the larger sphere catalyst for right now is giving us better results, but it's too soon to tell. In most cases, with most systems, you would buy some type of saltwater kit. And so it's tough to answer that right now. I will have an answer for that once we complete the remainder of these studies, because we also need to make sure that we get the same results for the lower end, for the drinking waters and the pharmaceutical waters. You know, just because this catalyst does really well on high salt samples doesn't mean it's going to be the optimum for those waters. So for now, you would have to buy a separate catalyst, and at this point, it doesn't look like you would need to buy a platinum screen or the quartz retaining ring. You would just buy a different catalyst. Is there any math between taking larger catalyst spheres and shortening time? I'm not sure what that, the only thing that I can think of, we need to look into that a little bit further. The only thing is that when you have a larger sphere catalyst in there, you have you have more, what I would say, interstitial spaces between the spheres, and therefore you may have a better interaction with the actual catalyst in order for that oxidation to take place, maybe a little bit faster. But I don't know if there's any specific math. It's more of the theory is that those spaces are bigger, which gives it gives it more of an ability to move in and out of those spaces and makes that oxidation take place. Is the needle rinsed in between sampling in addition to the sample loop? Yes, it is. So the entire sample pathway is rinsed. So your IC sparger and your sample loop and the sample needle. And the way that it does this is that the system comes with a 10-liter water reservoir. All right, I fill ours up with 8 liters of water, and it will last me a couple of weeks. It's under pressure. So when your air comes into the system, it goes through 2 regulators. One is a regulator to regulate the pressure for the water reservoir, and one is a regulator for the rest of the system that controls 200 mils a minute through the system. The water reservoir is under 12 psi, so that means that you do not have to change your water every day, and you do not have to worry about any contaminants possibly getting into that water reservoir and causing your blanks, causing your any system background to come about. So, and if you decide that you really want to go into the instrument more in depth, I can do that with you one-on-one and show you what the reservoir looks like. So yes, everything is rinsed in between, and in the schedule you can also add rinses. These do not use sample positions. So in the beginning of my run each day, the first line of my schedule is a rinse, and I set that to 7 rinses. I rinse it every morning just because usually by the time I run my samples, the system has been sitting for a while. Once you come in the morning, you push the ready button. That will click the carrier gas on. It takes about 15 to 30 seconds for the baseline to stabilize. And then I will start my run, and I'll start it with 7 rinses, then a blank, and the blank is what is used to subtract from your samples. And then I begin my run with all my check standard, 10 samples, and another check standard. The approximate footprint of the instrument, great question. It is 18 inches wide by 23.5 inches deep, and I think it's about 23.5 inches high, if I'm not mistaken. Let me just double check here real quick. 26 inches high. And that has to do with the sample needle that sits up there. And I don't think I have any more questions. If anybody wants to type any more questions and bring them over, we're coming up to the end. I want to thank everyone again for your time today. I hope this was very beneficial for you. Oh, we have another question. All right. It was mentioned that the TOC system can handle samples with particulates. Is there a limit to the amount of particulates the system can handle before the samples are diluted before analysis? So one of the things, very good question. Again, most systems, due to the tubing that is in the sample pathway, the particulates must be less than 0.8 millimeters. Now, if you have a lot of sediment, you may want to filter your samples before that. Just keep in mind that anytime that you have particulates, you are going to require more system maintenance. So it's the same thing with salt. Just like you will get a salt plug, if you have particulates, you will get a particulate plug that comes across. And you'll get to a point where those particulates are going to build up on the top of that catalyst. And it may not be as easy to dump, especially if it's sludgy or soil, some type of soil sediment or sludge, it might not be as easy to get that or dump that off the top of the catalyst. And of course, rinsing through the catalyst is not going to, be able to get that out. And eventually it's going to move. It'll find its way through the catalyst and possibly plug at the bottom. So you just want to make sure that there isn't a specific amount of particulate. The size is 0.8 millimeter. We are looking into possibly adding a mixing feature to this, but right now that is not available. So it just really depends on the amount of particulate that you have in there, and whether or not if you commonly or typically filter through your SOP, then you may still want to do that, because it's going to make your catalyst and your combustion tube and everything else last longer, including your calibration. I think that was the last question that I had. Once again, if you are interested in learning more or have some technical questions that you would like to ask me directly rather than on the group forum, please send me an email at Tammy, T-A-M-M-Y, .Rellar, R-E-L-L-A-R, @teledyne.com. This webinar will also be available up on the website probably in the next week or two. And there will be an application note coming out on this once Christina and I have finished the study. And hopefully you will all be able to join in for the next part of this series once we finish the remainder of the study, looking at a 200 microliter loop with each of our setups and configurations. Thank you, and I hope you all